So now a few words about the quantum function evaluation. So for this, it is actually quite instructive to look again at the Toffoli gate. Remember the universal reversible gate? When you look at the quantum version of the Toffoli gate, you see it as a controlled not operation. The first two qubits here, the two top qubits, control the third qubit. If both x1 and x2 here, so the bit value in the first and the second qubit is equal to 1, then you perform the not operation on the third qubit. Otherwise, you don't do anything. So the value, the bit value of the third qubit, call it y, it survives unless x1 times x2 is equal to 1, right? So whenever x1 times x2 is equal to 0, then the value of the bit value of the third bit survives. And when it is equal, on the other hand, when x1 times x2 is equal to 1, so when those two values are equal to 1, then you add 1 modulo y. That means you flip the bit value y, so you apply operation not. If you think about this gate operating implementing, for example, operation logical AND, what it does, it takes input x1 and x2 and gives you the logical AND, or the product in binary of x1, x2 in the last register, in the third qubit here. Just to see it explicitly is enough to set y equal to 0, then in this case you can see that you have value x1 times x2 stored in the third qubit. Or otherwise, if there is already another bit value in the third qubit, you simply just add the value of x1 times x2 to the third qubit. So this kind of idea will be now translated to the quantum function evaluation. So for quantum function evaluation, you can just imagine that we have many qubits as representing the binary string, or the value of x that we want to take as the argument for our function evaluation. So we are going to evaluate some function f that will just map the binary string of length n into 0 or 1. So for this, I just prepare two registers. I have the first register in which I store the value of x, and then I have the second register, in this case just a single qubit if it is a Boolean function of that type, which will store the value of the function. So then I will implement the function evaluation as operation on the two registers, which take the first register in state x, the second register in state y, to the state x, and I add to the value of y the value of f of x. So you see, very, very similar to the action of the Toffoli gate. What you can see that the value of x in the first register survives. So I have x1 here, and x1 at the output here, x2 here, x2 at the output here, and so on and so forth. But the value of the second register of this qubit here is just modified by the addition of the value of the function which we are evaluating here. So of course, you know, if we want to see explicitly what is the value of the function, it's convenient to prepare the second register in state 0, in which case we simply map x0 to x f of x. So that's how we evaluate functions. What is interesting is to combine the notion of the phase kickback mechanism with the quantum function evaluation, so that you can see that if we choose the state of the second register carefully, then we will, by doing quantum function evaluation, we will modify phases in the first register. In order to see that, in this case, it's enough to prepare this register not in some binary state y, but in state 0 minus 1. So if I prepare the first register in state x, but the second register in state 0 minus 1, So that means that I have the state which is a superposition x0 minus x1. And if I run the quantum function evaluation, then what I will get is x f of x from this term, right, minus x1 plus f of x, which now is equal to, and if you look at this expression, then you can see that there are only two possibilities here, right? F of x could be equal either to 0 or to 1. So when it is equal to 0, then you have x, and then you can just take 0 minus 1 and factor this out. If f of x is equal to 1, then you have here 1 and you have 0 here. So that can be written as in some sort of a compact way as minus 1 raised to the power f of x, and then I have state 0 minus 1. So when f of x is equal to 0, then the second register starts in state 0 minus 1 and ends up in state 0 minus 1, and nothing happens to the first register. However, if f of x is equal to 1, then the phase factor minus 1 is introduced into a given term in the first register. So this is, if you want to connect this with our discussion of the phase kickback, so this plays the role of our state u. And the unitary operation, so this is like a controlled unitary operation, except that this is controlled by different values of x. So depending on for which value of x that is stored in the first register, f of x is equal to 1. And for this particular term in a superposition, you have a flip, you have operation not. So this state here, this u is an eigenstate of logical not with a value minus 1. So if f of x is equal to 1, then you just do the flipping on the second register. If it is equal to 0, you don't do anything. So that effectively kicks back the phase in front of a given term x. So you will have a phase factor either minus 1 or plus 1. So that's your quantum function evaluation and the connection between the quantum function evaluation and the phase kick back to the first register. So it's worth having this in mind, and perhaps perhaps I should I just erase this and put state? Well, let me do it. So you can see that if I put state 0 minus 1 here, it survives as state 0 minus 1. But in this particular case, here you will get minus 1 f of x in front of x term. So that's how you introduce interesting quantum interference pattern to the first register using quantum function evaluation. So that's how it works. Let's see the consequences of this in analyzing few very simple quantum algorithms where we are going to use quantum function evaluation and the phase kickback mechanism.